All right, everyone. Welcome to our Chapter 5 kind of guided notes here. The first section of Chapter 5 should go by pretty quick, but we'll just go over the big formulas and the big ideas. So, we're going to start to talk about random variables and probability distributions of those random variables. And so, the first thing you should know is that a random variable is a variable that takes on numeric values with associated probabilities. So, that's kind of your definition. Maybe we should put that in bold. And so there are two types of variables we can encounter. We can encounter discrete or continuous. And really, in 5.1, we're going to be concerned with discrete variables as we go through them. Now, discrete means essentially countable or finite, or there's an easy way to essentially, maybe not easy as human to list out all the options, but using a computer software, like Excel, you could just say 1 and then scroll down to 1,000 and fill them all out in a second. Continuous is more difficult because it's real life values. And so what I'm kind of saying there is that you could always get more precision out of it if you had a better scale, something down to the microscopic level of height or something. But really, I want to say real life, and it could take on a range of values. So another way of saying it is, if you could express it as a decimal, you might as well call it continuous. Now, I'm sure there are a few exceptions there, but for the most part, that's going to be kind of your clue until you kind of get the hang of the idea. Now, I've already gone through and answered this because I don't feel like these should be too much of a troublesome question, but let's see what I mean. So the amount of rain during April, that would be continuous, and notice what I mean by quote-unquote real life there. So when rain falls, the weather will say we got 5 inches of rain, 7 inches of rain, but that's not true. They probably got 6.893 inches of rain, or they got 6.893271, blah, 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 but they rounded it up to 7 inches of rain because that just sounds better and it rolls off the tongue. But that's really a rounded estimate of a real life, there's always more precision you could have found value. So therefore the amount of rain would be a continuous measurement. It's a real life value. It's something that we can't count up. Up next, the number of people with blood type A and a sample of 43 people. Well, that would be discrete because a person either does or does not have blood type A. So we could easily just say there's either 0 or 1 or 2 or 3 or 4 or 5 all the way up to 43. Maybe all of them do. Is it likely? No, but is it possible? Yes. But the idea is literally 0 to 43 would be all of your possible values. No decimals, nothing else, because they're people. They either have blood type A or they don't. Political party affiliation, well, that wouldn't be a random variable at all because it's not a numeric value, right? That would be a what we call categorical, or it'd be described by a word, not a number. All right, and the number, if you did assign it to a number, it wouldn't have any meaning to it. You'd have to have a key to the side to define what it means to be a 1 in your political affiliation. All right. Up next, the number of light bulbs that burn out in the next week in a room with 20 light bulbs. That would again be discrete, and your answers would be either 0 or 1 or 2 or 3 or so on and so forth. The height of a giraffe, again, that'd be continuous because although you might say a giraffe is 17 feet, it's really probably 17 feet, 3 inches, blah, blah, blah. More precision you could always find. And then the time required to download a file, well, hopefully you know that one, and I'm just going to leave it at that. So, discrete versus continuous, right? Is it just a count? Is it really easy to see how you could list those people and check a box, yes or no, and move on? Or are you really trying to deal with some real-life measurements where you would likely round the number, but you really are talking about something more precise? All right. Just to throw it off this, or just to say it this way, if I even just say how old a person is, right? You might think, well, how old is a discrete measure, but really, how old someone is would be a continuous measure because you might be 35 years old, but 2 months and 7 days and 3 hours and 27 minutes, so on and so forth, right? Be careful about some of those things you're used to hearing as just rounded whole numbers, and think about, well, is that real life value, age, height, weight, whatever the other one was, amount of rain, right? Some volume measurement, anything real life, quote unquote, as I kind of said there, that's going to be your continuous. All right, moving on from there, we have probability distributions of our discrete random variables. And so it shows the allowable values and their associated probabilities, usually in some sort of table. Remember again, and this is already on the other page, but we're just reiterating, a random variable should have discrete numeric values in this section, and all those probabilities should add to 1. If they don't, then you don't have truly a discrete random variable. From there, we get two ugly looking formulas, but the good news is StatCrunch will do them all for us, but we will at least go through and show you how these work one time. So let's see what we're dealing with here before we really go any further. I got this one, or I blanked this one out and got it wrong so we could review it, but honestly, I don't feel like reviewing question 1 with you. Let's move on to question 2. So the first question is this a probability distribution? And to answer that, well, we're going to have to first ask, are these discrete numeric values? Yes. And do all these probabilities add to 1? And that's a little bit harder to figure out, but just from basic looking inspection, now you really should take a calculator and add them all up, but I do think they add up to 1. But let's be sure. Yep, great. Now from there we get a different question, which is what is the mean, or what is the expected value from this probability distribution, and what's the standard deviation? Now, we can, although this sounds super statistical and nerdy, you can bring some practicality to this and kind of look at these percentages, right? It's saying 0 occurs about 10% of the time, 1 occurs about 35% of the time, 2 occurs about 40% of the time, and 3 occurs about 15% of the time. So what values are you most likely to see? Well, 1 or 2. And particularly 2 is a higher probability. Now what that means is the true mean is, or the true expected value is not going to be 1 or 2, but it's going to be some decimal version. But that's again where we go from there's a precise statistical answer to a practical answer. But in other words, what we're doing is we're looking at this formula here. Now this formula looks gross because it does have that Greek E symbol again. Let me just put a space between those. But this formula is really just saying take every probability take every value and multiply it by its associated probability and add all those up. Now I'm going to go ahead and just do that for this one, but really all I did here was I took 0 times that value, 1 times that value, 2 times that value, 3 times that value. Type that into your calculator carefully and you should get 1.579. Now I'm also glossing over that because we are about to see this answer pop up in StatCrunch with 0 effort, but what I want to do more so is let's look at this uglier formula and see if we can make sense of that. So this formula is saying take every value and compare it to the mean, square that, then multiply it by its probability, add all of those up. Whoa, and then put it in a square root. So that's a much uglier formula. Let's see how that works practically. Again, StatCrunch can be used the whole way through to this problem, but let's at least just see what's going on here. So I need a square root, and it's the square root of each value, so 0, compared to the average of all my values, square that, and multiply that by its probability. Then I have to add that to 1 minus the mean of all values, square that, multiply it by its probability. And at that point I'm going to write plus, and I'm going to write dot dot dot, essentially. Oh my goodness, what's going on here? There we go. And trust me, when you work all that out, well, let me work that out for a second off screen. Alright, when I ended up typing that in, I got 0.867 as my standard deviation. Alright, now let's see what happens here for us. let's see, are those the same numbers? 107, 352. Well, they'll be a little bit different, but we can go ahead and correct that. Now, let's show you how to do this in StatCrunch. The good news is you can see you can copy that data set exactly when you open it. Now, I need to copy it to what I have here in my notes, not to what the homework question is. Give me a second. It's now 0.107. It's 0.354, 0.392, and it's still 0.147. Great. All right, now how are we going to figure this out? We're going to go to Stat, we're going to go to Calculator, and we're going to go to Custom, and we're going to say that X are my values and the P of X is my weights, and I'm going to write Compute. Now right there you can see my mean and standard deviation are given to me, and then you have this whole other chart on the bottom that we're not even actually making any use of at all, but you can see there's your mean, there's your standard deviation. So it's the same answer, but hopefully you tried it out and just went through the hard work once, right? I think it's worth your time to try typing in the whole formula and see if you can do it, and then appreciate StatCrunch that you can again go to, where was it? It was in Stat Calculators, and you're going to the bottom to Custom, because again, this is not the normal distribution. It's not the binomial that we're about to learn about. It's its own special one because it's its own discrete random variable. Your values are your x's. Your weights are their probabilities, how likely they are to occur. And again, there's your mean standard deviation for free. Awesome. Now from there, the question starts being, well, how do I use this table that I have? How can I use it to answer some questions? So once again, what you could do is you could, use StatCrunch, but for a few of these, if you have the whole table and the numbers aren't that big, really it shouldn't be that hard to just calculate these out yourself. So, for instance, this says they want exactly 6 girl births and 8 births, and so, well, what are you going to do? You're going to, whoops, that went way off track. You're going to, why is it doing that? There we go. Just literally circle that value, and you're going to get 0.102. And you're done. That's the probability, because it literally is an exact value on the table there. So let me maybe make that a little bit smaller. There we go. My computer screen's at an angle, so it's throwing me off whenever I write it out. Anywho, so about 10% chance. So we're just reading the table. Exactly 6 means find the item 6 and circle the answer. Now find the probability of getting 6 or more. Different question. 6 or more, well, would be 6, 7, or 8. So guess what you're going to do? You're going to take your 0.102 and you're going to add the next probability, the 0.019. And then you're going to add the probability of the 0.004. And whatever that ends up being, I'm just going to put a box around it, but you'll need to work it out. Whatever that is your final answer. The one thing I want to say is they'll then say, would it be, the C question that I don't love to cover all the time is going to be, is it surprising to see 6 births? And the way you answer that question is by using the second of the two, which seems counterintuitive, but I want to remind you of this, that a p-value or significance is based on getting your result. So even if they're asking, is 6 high? You're saying, well, what is the probability of 6 or more? And that's how you'll determine the true answer. So kind of counterintuitive, but again, take a look at that slide. Significance is based on getting your result or the resulting question or something more extreme in a more extreme direction. So 6 or more births. Is that high? High is dictating that value or more. And there we go. Okay, so there's a lot there, but really that's about all that's going on in this section is you've got some charts. Can you find the mean and standard deviation from them? Yes, it'd be tedious. Multiply, 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 combine, 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 combine. There's your mean. Use that mean with this whole other wacky formula, which would take forever to write out, but StatCrunch is there to save us. Imagine if you had to do that with this one, that would be just awful. And so then we dive into 5.2 already. and we talk about the binomial distribution. So there's three defining characteristics of the binomial distribution, and that's why sometimes you'll see the binomial distribution lazily written out as B parentheses some number, some number, some number, like you kind of see here. And the some number, some number, some number is the number of trials, the probability of success, and how many trials you were wanting to be successful. So let's break this down and talk about what does it mean to be binomial. Well, it means you're doing something a fixed amount of times. So maybe you're flipping a coin 7 times. Maybe you're asking 43 people a yes or no question, something of that sort. But you know how many people you're asking, you know how many times you're going to flip the coin, etc., etc. From there has to be 2 outcomes, heads or tails, yes or no, in favor, against, candidate A, candidate B, whatever you want to think about there. From there, every time you ask someone, it should be assumed that when you ask someone or flip the coin or whatever, that anyone's previous answer shouldn't affect anyone's next answer, or any coin flip in the past shouldn't affect the coin flip in the future, which should be true. And if that is true, then that number 2 means the probability isn't changing as you redo your question or coin flips. So that's why we highlight P as well, because the probability should never change based on a prior result. So N is fixed, I know how many coins I'm flipping. P is fixed, I know the probability of having someone be in favor of party A or not party A. And then X is how much am I trying to get out? How many people am I looking for in favor? How many heads am I looking for in my coin tosses? So there we go. Now the formula for it, to find the exact amount, is pretty ugly. It looks like this. Now the short form would be this. Notice what this is using is it's saying, hey, the complement 1 minus P, 1 minus getting a success, in other words, the probability of failure, we're just going to call that Q. And this formula looks pretty nasty, and it's also saying, hey, this NX is not some sort of weird fraction. It's actually your old NCX formula, your combinations formula that we learned how to do on the calculator, the NCR, so to speak. All right, so we've got a lot of formula to deal with here, but the good news is StatCrunch will do this all for us. So really, I want to do one example together and then fly through your StatCrunch your homework with StatCrunch. All right, so let's look at this kind of question together, and then we'll dive into your homework. So we're going to use this question to kind of show you where this really wacky looking formula is coming from and why every part is here. So without further ado, here we go. If a basketball player makes free throws 73% of the time, find the probability of them making 2 of the next 6 shots. So the idea is someone's going to take 6 shots in the game. And we want to know, what is the likelihood that they'll make 2 and they'll miss 4? And as we work that out, right, we're going to move from my crappy writing to writing this as formulas. Let's translate that into, well, that would be making a shot is 0.73, and missing a shot would be, and this is where the complement comes in, the Q comes in, 0.27. Now I'm going to go ahead and copy that. And there we go. Now from there, we can be an even lazier mathematician, and we can then say, well, wait a minute, that would actually just be 0.73 squared, and then that would end up being 0.27 to the 4th. And I'm just using exponent rules that says if something's multiplied together twice, I can just write that as squared. If something's multiplied together 4 times, I can write that as to the 4th. Now I'm almost done, right? If you look at this, what I have is I have my P squared, my successes squared because I'm only making 2 shots, and then I've got 4 misses because there were 6 shots and I already used up 2 of them because I made them. So there's 4 shots, exponent 4, of the probability of a miss because I won't make it. Now this is almost correct, and this is kind of your first question, which I'm glossing over, but teaching here is this is not enough to be your final answer. Why? Well, because I haven't taken into account this nx. But why does that matter? Is the question. And so what we need to write is we need to say if we just stop here, we only calculated making the first two and missing the next four. We didn't calculate making 2 out of 6 in any of the orders those can occur. I guess not any, but all. So we just want to be able to make 2 shots out of 6. And the idea is this is only one way that happens, only one outcome. And so the last thing to say is the combination out front takes care of this. So in other words, that combination is going to do that heavy lifting for us, and we're going to write it down. Oops. Down here. So now we're going to say what I really need is I'm going to write it like this. Let me get my equation tools back out. Let me get the brackets. I'm going to use that lazy bracket because I can't really write the NCX easily on here. I don't know why it's not showing up. There it is. So I'm going to write the 6, choose 2. In other words, how many different ways can I have 6 shots and make 2 of them? Well, the amount of ways that I can have 6 objects and I collect 2 of them out is, well, 6 NCR, and you can find that button on your calculator somewhere, 2, and it ends up being 15 times all that stuff. So, in other words, and you should do this at least once as kind of an exercise to yourself, it turns out that there are 15 different ways you can put 2 Y's and 4 N's together in some order. So swap them around, switch them around, put the Y's apart from each other, cycle the 2 next to each other all through the N's. Other things like that. It turns out there will be 15 different ways you can do that. And so this is your final probability. And let's write out what this is. Let me work it out. I haven't done it yet. So I'm typing it into my calculator, but you're just hearing me talk about it. So 15 times 0.73 squared times 0.27 to the 4th, I get 0.0425 if I round that to 4 places. Now, maybe the question is, why is that probability so low? Can we bring some sense to that? Well, think about it. If they do make about 73% of their shots, then just on average, and there still is a mean and a standard deviation to the binomial distribution, but on average, I would expect in 6 shots to make about either 3 or 4 of them, or actually, sorry, about 4 or 5 of them, because after all, 4 out of 6 is 66%, and 5 out of 6 is 83%. So I would expect that I would make 4 or 5 of my shots, because after all, I make the majority of my shots. So making only 2 out of my 6 would actually be kind of rare if you think about it. If I should make about 3/4 of my shots and I make 33% in a game or something like that, then really that should be an unfavorable or unlikely outcome. But all in all, I hope you kind of see the idea of the build-up here is we did say, okay, I want 2 out of 6. I want 2 yeses, 4 nos. 2 yeses, 4 nos. Notice how the yeses and nos end up being your exponents, and your probabilities use the complement, right? 1 minus. From there, we need to throw in that combination. What is 6, my total options? Choose 2, how many successes I want. In this case, that ended up being 15. And there we go, there's your probability. Now, you can't, just to say out loud, you can't use that kind of reasoning of saying, oh, well, if I usually would make 73, then I can just arrive at this number quickly. Obviously, hopefully, you see that this formula is really involved. It makes use of these probabilities. It uses them in ways that maybe don't seem intuitive, but hopefully with a few more time and practices or other homeworks, it will make sense. So with all that being said, Let's now dive to your homework and once again see how StatCrunch can make use of all this. But, oh wait, before we do that, we got to do one more slide. We got to find one more thing about the binomial distribution. We need to calculate or let you know what the calculation is for the mean and standard deviation. And first, it's literally what I said. This is why I kind of said, hey, what happens if you make 73% of your shots? Well, then you would expect literally to just take the amount of shots you would make and multiply it by that number, which in that case ended up being about 4 or 5 if you do the math there. So literally, if you take 0.73 to go back, if you take 0.73, your probability, and you just multiply by how many shots you're going to take, you get 4.38. So again, you would expect somewhere between 4 and 5 shots on average. Now your standard deviation is going to be a little bit different. It's still going to involve a square root though, but it's going to be n times p times q, all in the square root. So really simple formulas there, but again, guess what? StatCrunch can do those all for you. But just so you know, the binomial distribution does have a mean and a standard deviation as well. So with that being said, let's now open up your homework and see how StatCrunch makes this all way easier for us. But hopefully you reviewed where your combination button was on your calculator, and hopefully again this formula, piecing this formula together makes sense. I just want my 2 yeses and my 4 nos, but then I need to take into the account the order that those yeses and nos could come in. I want all of them, all the orders, because at the end of the day, I just care that I made 2 of my next 6 shots. I don't care what order they're in. I need to write out some order to make the formula work, but then I say, well, now I need all of them, but it will still be 2 yeses, 4 nos. Okay, there's a lot going on there. Again, pause it, think about it, let that set in, rework it out. And again, I also highly recommend listing out the ways you can write 2 yeses and 4 n's and end up with 15 different ways. See how that ends up making sense. It's a good exercise for you to do. Let's do your homework. All right. Now, this first question, and I'm going to skip over the first few because I want you to try those out. I think it's worth your time. So we're going to start on question 5 together and get straight to the math, but I want you to work through those other ones. I think they're good practice. The one last thing before we do StatCrunch is I do want to show you this very wacky, ugly table and show you that it can be used to answer these questions, but we will use StatCrunch really. Now this table is kind of blurry and it's not easy to see, but notice there's an N, an X, and a P. Hey look, all the things we talked about in the formula. And what I see is that we have N trials, which is 7. We want 4 successes, so 7 and 4 are my numbers that I'm looking for here and here. And my probability is 0.6. So if I look at all those together, it's kind of wacky, but here's 0.6, so I know I'm zoomed into this column. I'm going to scroll down until I get to, and notice I'm keeping my mouse here on the 0.6, but where is 7 and 4? 0.6, 7 and 4. So here's 0.6, gotta keep my mouse there, and then if you look on the left and right, there's, whoops, and I just lost it, gotta go back, there's 0.6. If you look at the left and right, I got down to 7, and then I'm going to go find 4. There it is, 0.290. I just answered the question. So that's pretty convenient. There's really no work to be done if you know how to read that chart. But let's just see how we could do this with StatCrunch instead. Alright, we don't need anything here other than to go to a calculator and say that I want the binomial calculator. From there, well, what did I want? I wanted, out of 7, and a probability of 0.6, I wanted exactly 4, and there it is, 0.290 as well. So, pretty cool, you can do it either way. So, for that last question again, it was it was stat calculators and binomial. We choose our n, we choose our probability, and then we read the question to figure out, did I want exactly 4, did I want less than 4, did I want greater than or equal to 5, so on and so forth. So let's read this one. 39.8% of consumers believe that cash will be obsolete in the next 20 years. Assume that 8 consumers are selected and find the probability that fewer than 3 find the probability that fewer than 3 believe that cash will be obsolete. Now, one thing to watch out for, but it hasn't happened yet, is make sure that they aren't negating the question on you. So it says 39.8 believe it will be obsolete, and they want that you actually find fewer than 3 will be obsolete. So the words match there, so just be careful about that. Now it said 8 consumers, and from there it's saying 0.398 probability will think it'll be obsolete, and I want that fewer than 3 think it will be obsolete. So fewer than 3 means less than 3, not less than or equal to, but strictly less than 3. Fewer than 3 is 0, 1, or 2. This has x is less than 3, so 0, 1, or 2. And there's my answer, 0.319, or I guess 0.320 when I round that to 3 places. So we're just reading the question and going right to the StatCrunch binomial calculator. All right, up next, same idea. 48% that they should say that job applicants should follow up in 2 weeks if 8 human resource managers are selected. Find the probability that at least 2 say that they should follow up. So same idea. There's 8, so that was nice that that's still the same. Now this changes to 0.48. And I want, that at least 2. So that could be greater than or equal to 2. And that would be 0.955. So really, you're just reading the words in the question. You're diagnosing what's my N, how many people am I selecting, how many trials am I doing, what's the probability that's not changing every time. And then you got to just make sense of what does that mean, at least 2. It means 2 is included, it could be 2 or more. And for this, that ended up being 0.955. All right. At that point, I don't feel like I need to go through this question. I think you could do that. Why not? We'll do it together. So, 37%, there's my new probability, 0.37. Said that human resource professionals at companies that reject candidates because their information's found on social media. If 25 human resources, so 8 now is 25, are selected, would 14 be high that they rejected job candidates because of information they found on their social media? So would 14 be significantly high? Now think about what we just said on a little bit ago. Significance is based on 14 or more in this direction. And it even says that here, 14 or more in all your choices, so that's there to guide you along. So 14 or more, greater than or equal to 14. That is 0.041. And would it be significantly high? Yes, it would. Because, they want that to 4 places. 0.412. Now, why would that be significantly high? Because the likelihood of that happening is less than 5% of the time. And because its likelihood is very low, it means this result is significant because it's very rare. It's kind of like a flipping on the words there, but again, because the probability is so low, to get this value would be significant. Interesting. All right, I've got one more I really want to cover here, and it's just that mean and standard deviation question. So, let's see here. I wonder if we could even do that. Stat, calculators, summary stats? I don't think it would necessarily be there. I think this is one that you're actually just going to use a calculator. So let me get that pulled up. All right, so it says, assume that they were trying to increase the likelihood that a baby would be a girl, but assume at the beginning that there's no effect to this method. So if there's no effect, and you're going to have 26 couples try to have a baby, and the regular probability is 0.5, because again, that should be about half and half. Then at first we've got 26 couples times half and half, that would be 13. So there's me using that formula that we talked about. Whoops, where'd it go? Right here. Just 26 couples times the probability that you were after should be what you should expect in a trial. All right. Up next, what would the standard deviation of that be? Well, it's almost the same formula, but now there's a square root, and it's 26 times 0.5, the yeses, or the I got a girl in the birth, and then times the no's, or in other words, I got a boy in the birth. And that is 2.549, but they want only to one decimal place, so 2.5. All right. So that's the mean and standard deviation based on assumptions. And now we're going to use the range rule of thumb, if you remember that. The range rule of thumb says, hey, don't use any of those wacky formulas. Just take your mean minus 2 of your standard deviations. That's 8. Oops. And then do the same thing, but make it a plus to find the significantly high. That would be 18. All right, so 8 and 18 are now our fences. And so is the result of 22 significantly high? Well, remember what it means to be significant in this case. Think about fences. We're in Ocala. There's cows all around. If a cow's in your fence, that's fine. If a cow's outside of your fence, that's significant. So because 22 is outside of the range of 8 to 18, then the result is significant because it's greater than 18. It's greater than the upper fence. So that would mean it is effective. So if you read the whole question in context, the goal was, can we increase the likelihood of having a girl? And, well, if we couldn't, if there was no effect on whatever method we were trying, then even though we would expect 13 out of 26, half and half, to be girls, there still is standard deviation. There still is randomization that happens. And so really, 8 to 18 would be normal or typical expectation of what you would expect to see, even though 13 is in the dead center. Right? That should remind you of the normal distribution and the empirical rule. From there, 22 falls way outside of not just dead center, but outside of moving that dead center 2 standard deviations below and 2 standard deviations up. And so because it does fall out of the fences, it's significant because if your cow's out of the fence, you better go find it. All right. At that point, we've gone through pretty much everything we need to from Chapter 5 together. I hope this was beneficial to you, and I'll see you for Chapter 6.